Hi everyone, this is Elif Gozen from FORD OTOSAN, Turkey. Our project is Thermal Management Model Development and Fuel Cell Powertrain Optimization in Coach application. Sencer and I will present you our studies on the fuel cell systems. Outline of the presentation is shown. We will start with introduction and then section 1 and 2 will be presented to summarize completed studies. Then we will continue with the conclusion and next steps. Introduction. Coachified is an Europe-funded project that aims to demonstrate the evaluation of the fuel cell city bus drive systems in the coach sector. FORD OTOSAN supports the generation of the thermal management system design, virtual demonstration, system optimization, and testing activities. The developed knowledge within this project will be applied to FORD FMAX with fuel cell powertrain. Goals of the thermal management system studies are generation of thermal management system model of coach, running layout iterations to finalize thermal management system, powertrain design and control guidance in the early phases of the project. Goals of the powertrain optimization studies are generation of fuel cell powertrain and vehicle models of truck, improve fuel cell control algorithms, state and transitions based on energy consumption results, and providing design and control guidance in the early phases of the project. In a nutshell, fuel cell is an electrochemical cell that converts the chemical energy from a fuel into electricity through an electrochemical reaction. Fuel cell type in the modeling study is polymer electrode membrane fuel cells. And fuel cell powertrain topology of this study is shown. Section 1. Thermal Management Model Development. Thermal management studies are started with generation of the requirement list, and then reference thermal management model is generated based on Autocar e-bus, components and layouts. This is the bus considered as reference system. It is fully electric bus. Battery cooling and heating circuit and powertrain and auxiliary circuit model views are shown below. After modeling of reference thermal management system, fuel cell thermal management system layout is studied. Literature survey and reference system layouts are considered in process. Fuel cell circuit, powertrain and auxiliary circuit, and battery cooling and heating circuits are generated. In the fuel cell circuit, fuel cell model, which includes fuel cell stack, coolant pump, aftercooler, humidifier, DI filter and filter. HVAC heat exchanger is placed to use waste heat of the fuel cell stack in cabin heating. System is cooled down with radiator and fan. Powertrain and auxiliary circuit includes e-motor, drive inverter systems, power electronic components, and fuel cell module auxiliary parts. System is cooled down with radiator and fan. And then we could see battery cooling and heating circuit, which is rely on the reference cooling system. GT model of fuel cell thermal management circuits are shown in 3 circuits: battery cooling and heating circuit, powertrain and auxiliary circuit, and fuel cell circuit. Up to now, 2 iterations are completed. Since iteration 1 results are not acceptable, iteration 2 layout is studied. The roadmap of the thermal management studies are: reference thermal management model is generated based on Autocar prototype e-bus layout, and component data is received from Autocar. Component pressure drops and flow rates, component heat rates, pump maps, heat exchanger cooling capacity, active and passive cooling of course, are provided. In second step, model is correlated with the test data provided by Autocar. Flow rate measurements, component inlet and outlet pressure measurements, component inlet and outlet temperature measurements are used. In third step, coachified thermal management simplified model is generated based on reference thermal management model. the fuel cell circuit and fuel cell components are added to the reference thermal management model. Afterwards, layout iteration study is started. Target is meeting all system, pressure, flow rate and temperature requirements with minimum water pump and heat exchanger power capacity. As you could see, the reference model simulation results are compared with the test data. 2% accuracy is targeted for volume flow rate and pressure. Correlated model meets the flow rate and pressure results in 2% accuracy. Battery circuit heat exchanger volume flow rates and inlet pressures are shown. For the powertrain and auxiliary circuit results, you could see auxiliary radiator inlet volume flow rate and radiator inlet pressure results. When we come to the iteration 1 and 2 for the fuel cell circuits, battery cooling and heating circuit results are nearly unchanged, since only PTC heater is added in the circuit. Therefore, there is no modification is required as long as battery type, battery pack number, etc. is unchanged. Iteration 1 and 2 battery circuit results are same, as shown in the graph. When we investigate powertrain and auxiliary circuits, reference model is capable of providing required volume flow rates per components. But after adding fuel cell auxiliary pack, powertrain and auxiliary circuits, system resistance increases. Hence, the water pump flow rate decreases in iteration 1, as shown in this graph. In order to decrease the system resistance and meet flow rate requirements, iteration 2 is studied. Water pump power and radiator cooling capacity should be studied further to meet flow rate and temperature targets. Due to decreased volume flow rate, e-motor inlet and temperature increase in iteration 1 and 2 when we compare with the reference model results. In the next iterations, water pump power and radiator cooling capacity should be updated to meet flow rate and temperature targets. Fuel cell circuit is generated based on available limited information in the early phases of the project. First results show that the current radiator is capable to provide coolant temperature below 70 degrees C for fuel cell module.
Hello everyone, this is Sencer. In this section, I am going to talk about fuel cell powertrain optimization in truck application. As you see, there are several subsystems like fuel cell, battery, electric motor and vehicle systems are created in GT Suite example model. The modeling assumptions are listed with the table. I'm going to mention about them. Fuel cell stack rated power is limited to 200 kilowatts. Fuel cell operational maximum power is 160 kilowatts. Electric motor maximum power is 320 kilowatts. Different battery capacities are used like 24, 36 and 48 kilowatt hours. Vehicle mass is 27 tons. In this study, there isn't any thermal solution on the system. The vehicle control algorithm can be created with finite state manager object in GT Suite. Each state refers each vehicle operation mode. The base algorithm has 5 states and 9 transitions to switch between these vehicle operation mode states. The new developed algorithm has 6 states and 15 transitions to switch between these states. Briefly, I would like to explain them. Let's look at the base algorithm. State 1. Normal operation mode means only fuel cell power is enough to vehicle power request. State 2. Fuel cell operates above the vehicle load request. The margin can be used charging battery. State 3. Fuel cell off and only battery is used for vehicle load request. State 4. If the vehicle load request exceeds the fuel cell and battery power, fuel cell and battery operates together. State 5. If the vehicle load request is negative, it means braking request exists, recuperation mode is activated. The new algorithm has the additional sixth state. With the state 6, fuel cell charges the battery during soft recuperation actions and critical battery level via using the battery charging power margin. In this slide, base and new algorithm results are compared. For different initial SOC values, as you see, the base algorithm fails at low SOC values because the fuel cell cannot provide sufficient power and transitions cannot switch to the proper state. In these graphs, negative values in battery electrical energy consumption refers energy gains with recuperation end of the cycle. When we look at the y-axis of graphs, it's shown that the new algorithm and transitions give better total energy consumption under the same condition. The graph at right hand side means if the system operates battery weighted, the total energy consumption reduces because the fuel cell consumes more energy due to the energy conversion. In this slide, I'm going to talk about the transition rules. Transition rules decide that when the vehicle operation mode, that is called state, should be changed. This study is performed with approximately 700 kilometers on-road fuel economy cycle and the results are shown for 48 kilowatt hours battery capacity. I would like to explain SOC A, B, C values. These are SOC thresholds of transition rules and totally 3 thresholds exist in our algorithm. It's clear that when the transition condition values decrease, the total energy consumption value also decreases. Below a certain value, the decrease in total energy consumption becomes stable. Initial SOC values are examined for different battery capacities and 70% initial SOC values implemented for transition optimization study with 48 kilowatt hours battery capacity. The transition studies took place for many cycles and as a result, since the FORD label is the label with the lowest total energy consumption, the values here were chosen for the new algorithm. As a result, the new algorithm, which has new state and transitions, and the transitions are rearranged compared to the base algorithm, has 18% better energy consumption and 28% better hydrogen consumption at on-road fuel economy route. Now, my colleague Elif Gozen will continue. Thank you.
And now we will continue with the conclusion section. In this study, thermal management system design and fuel cell operation algorithms are investigated and optimized. Thermal management models are generated. System layout iteration studies are in progress, and it will be finalized when all component selections are done and all requirements are met. A new algorithm is created by adding new states and transitions in order to reduce energy consumption. The new vehicle operation mode, battery fuel cell energy source usage, algorithm which has new state and transitions are rearranged compared to the base algorithm has better energy consumption and approximately same hydrogen consumption on the road fuel economy road. In studies on battery capacity, it has been observed that as the battery capacity grows, the total energy consumption decreases and the consumed hydrogen amount also decreases. Similarly, increasing the initial SOC value lowers the overall energy consumption. In the next steps, Thermal management system layout iteration study will continue until all component selections are done and all requirements are met. The new vehicle operation mode, battery fuel cell energy source usage algorithm will be implemented to the coach fuel cell vehicle model and energy consumption will be reported. FORD OTOSAN is planning to demonstrate a new F-Track variant with fuel cell powertrain within next year. The developed methodology will be implemented to the product development cycle. Thank you for your interest. If you have any question, we would like to answer.